Let's look at transforming functions here. So this f stands for essentially any function that we could have. Okay, so that could be squared, which is quadratic. All of this could be a root, could be an absolute function, could be cubed, could be the power of 1. What's the power of 1? Anyone know? Linear. Anyone remember that? It's linear. Okay? Power of 1 is a linear function. You just never write the 1 in. Okay, I've already digressed. Okay, so the function here. And this function, this square bracket, is supposed to let you know that anything under here is kind of like under an umbrella of the function. Okay, so let's talk about what's outside the function first, because it'll be a little easier for us to make sense of what's inside after. So the a is outside of the function, and so is, get the purple here we go, so is our c. Okay, if c is positive, we go in a positive direction when transforming the function. We move it upwards. If c is negative, we go downwards in the function. So it's pretty intuitive. It's exactly what it says it is. It's okay, I'm still recording here. Saying c is intuitive. And the same idea is with a. If a is greater than 1, we have a vertical stretch. So it's supposed to get thinner if it's a parabola. That's the concept. But it's being pulled upwards and downwards. Think of it like, I can't see the front, there you go. Think of it like it's an elastic band being pulled from the top and the bottom, so it gets thinner and thinner. Okay? And if a is less than 1, or sorry, I should say the absolute value of a. If the absolute value of a is less than 1 and greater than 0, it's being pulled, it's vertical, not horizontal, so I shouldn't have the arrows that way. It's being compressed. Slide down. There we go. I don't have my normal stuff here. It's being compressed. Again, think of it like an elastic band. If it's being pushed from the top and the bottom, it'd be getting wider and wider. Okay? So these are intuitive things. These are what you would think would probably happen with these types of values. Everything under the function, or within that umbrella of the function we talked about, is kind of the opposite. If we have a positive value here, okay, and everything under is horizontal, everything outside is a vertical movement, everything inside is horizontal. If we have a positive d value, then you think of it like we're going in a negative direction to the left. If we have a negative d value, we're going in a positive direction to the right. Okay, and this one's probably the most confusing, is horizontal compressions. If you have an absolute k value that should say greater. Okay, if it is greater than 1, okay, it's actually being compressed horizontally. Okay, so again, think of it like an elastic band that's being pushed in at the sides, and that idea is actually very similar to a vertical stretch. Okay, and our opposite of that, if the absolute k value is less than 1 but greater than 0, it's being horizontally stretched, pulled out this way. Okay, so it's being pulled. Wait a second. This k, again, when we have an a value, if it's greater than 1, we would normally say it's been vertically stretched. Say the value is 3, we say it's vertically stretched by 3, by a factor of 3. Okay, and if it's something like a half, we'd say it's vertically compressed by a factor of a half. Okay, now with the k, we kind of do the opposite idea. If the k value is the number 3, we say it's horizontally compressed by that reciprocal, so by a factor of a third. Okay, and if it is a third, we say it's being horizontally stretched by a factor of that reciprocal, and that reciprocal would be the number 3. So why does that happen? Well, we could tie that to mapping notation. So we're just going to really focus on this with mapping notation. Mapping notation states that x, the new value of x, is equal to the old value of x plus d. Okay, again, the opposite kind of what's in here, and it's divided by k. Okay, so this divided by k, we're going to put these two factors in, our 3's. Okay, so if the k value is equal to 3, okay, what ends up happening in our mapping notation is we're taking the old x value and we're dividing by 3 here. Okay, and when we divide by 3, you could common factor this out. It's the same as multiplying by a third. So that's where we get that idea of changing it by a third instead of the factor of 3. If the k value is equal to a third, and we put it into our mapping notation, the new value of the x is equal to the old x value divided by a third. Okay, and that can be a little confusing, but we're going to go into our fraction rules here. I'm just going to really just focus on this part here. our old x value is being divided by a third. Okay, so we have to divide fractions. You guys remember dividing fraction rules? How do I turn the old value of x into a fraction? Put over 1. Great. And I need to divide. What can I do to divide these fractions? We multiply the reciprocal. So we turn it into a multiplication question, and we flip this. Still in blue, yeah. 3 over 1. And we get 3 times the old x value, which is the idea of horizontally, it's going a little slow, of horizontally stretching it by a factor of 3. So that's why we get those opposite ideas with decay. That happened again. I'm still recording, okay? I think that's